Hello everyone. Welcome. Good evening. Welcome to this problem solving session. So we will start now. So I hope I am audible. So if you have any doubt from the previous session, you can ask. I will pause for some time. We will start by summarizing this week content, and then I will solve some problems related to this week content. Whatever the previous year assignment problem. And yeah, so I'll pause for the time, and if you have any doubt, then you can ask with related to any content, whatever covered in the lectures or in these tutorials or uh, whatever covered in the previous session in this session also. So this week content basically discusses about the metal semiconductor junctions. So basically this metal semiconductor junctions, and the other was the MOS capacitors and different regions of operation of the MOS capacitor. So let me first summarize what are the metal semiconductor junction. So the content is metal semiconductor junction. So why those metals and semiconductor junctions are important? Uh, why these are important? So basically, even if you consider a discrete component, so your external leads are are of, if you consider any transistor or anything. So external leads are metals. So that's because they like the conduction of the metals is resistivity is quite low, and that's why there is low potential drop, low resistance, and low signal loss basically is there. So that's why you need as better metal as possible to connect to the external world. So basically, uh, the you can't use any semiconductor because that has comparatively lower resistivity, and if you want to route a signal to larger distance, or even at the wafer level from one corner or one device to other device, if you want to connect, then you want to use as low resistance as possible. So to make those external connections, so you need to make the you need to connect the semiconductor with metal. So just wait. Yeah, so you need to make external connections, or within the wafer. Suppose you want to connect two different devices, then also you need metal wires or metals like metal lines. You need even on chip you need lines. So that you need metal connection. So that's why those metal semiconductor junctions are important. And if you and that is not that is not as simple as like if you are joining two same material, which makes proper contact with the semiconductor. Sorry for the bad connection. Yeah, let's just get started. Yeah. So that like to make an external connection, basically you need the metal semiconductor junction, and it's not that simple as you make the context of two similar metal or two different metals. So we will see the detail, and as you have seen in the details in the lectures also. So we let me just summarize how the metal semiconductor junctions are. So how the metal semiconductor junctions you make. So basically you take a silicon wafer, and on that basically you deposit a metal. And on that you deposit a metal, and on the selective area you remove that metal, and you make a pattern. Suppose if you make a pattern, just hello, हाँ शिशिर. हाँ हाँ. Yeah, I'll share. I'll share. Okay. Just okay. So yeah. Sorry for the glitch. Yeah. So basically, what you do, you remove this metal selectively from certain areas, and then like if you take this metal, if you remove, then basically it will become like this. So it will become like this. Here the metal is there, and here the semiconductor is there. So if we take the cross section of this junction, so basically then it's from the metal semiconductor junction. And so we can draw the energy band diagram of the metal semiconductor junction. And before that, some parameters are important. So if we draw, so so in the metal, basically your Fermi level is the main level, and below which like almost all the states are occupied, and above which all the states are empty. And so suppose and then there is one parameters. So this is known as the work function. So this fire. So what is like how the work function is defined? So basically, this was invented like given definition in then those times when like the vacuum tube kind of thing used to be there. So so the work function of the metal is defined as the energy required energy required to eject out an electron from the surface of metal. To eject an electron from the surface to a vacuum level. So basically, vacuum level is like suppose you are ejecting out electron from the metal, and vacuum level is just at the when the electron is the kinetic energy or energy of the electron is just at the zero. That is known as the vacuum level, and that this energy is known as the work function. And since in the metal, like the only the important level is the Fermi level, so so this is one of the important parameter. Also, so this is the vacuum level. So so this vacuum level, you can also draw the semiconductor band diagram. So in the semiconductor, we are drawing this separately. We have not yet made the connection. So this is so one important parameter is so here also like the so this is work function, and similarly if with respect to EF and vacuum level, so this is vacuum level. So you can define work function of semiconductor. And also like one more material, this is the work function of the semiconductor is basically dependent on the certainly the material property, which kind of material you have taken, and also this because the Fermi level changes with respect to uh, with increase or decrease in the doping concentration, so work function changes accordingly if you do doping or if you change the property of semiconductor. But one more important parameter is defined as electron affinity. So this is chi. So it is the similar electron affinity which you have studied in 10th class or 12th class for chemistry in the context of uh, uh, atomic structures. So basically, electron affinity is the energy required to eject out electron to move an electron from conduction band to the vacuum level. So the chi is related to the the conduction band to vacuum level. So if you draw the band diagram, so if you draw the band diagram, then basically then what is this is the Fermi level phi of metal, work function of the metal, and depending on the which kind of doping is there, you can define this as phi of semiconductor. Just hold. Hello, hello. नहीं, अभी मैं बिजी हूँ, कुछ टाइम बाद कॉल होगी। 2 hours. या। हाँ हाँ, ओके फाइन, ओके। Hello, yeah. So this is the semiconductor Fermi level, and then you define the uh, electron affinity chi, and that is material dependent parameter, and you define a the Schottky barrier as the phi b, which is like the Schottky barrier, and which is defined as phi of metal work function minus chi of semiconductor. So that is defined. So so now basically now if we draw the band diagram with the so there are different case of ohmic like the metal semiconductor junction. So so in your in your like the two type of contacts exist in the metal semiconductor junction. One is ohmic contact. So ohmic contact or Schottky contact, which are on also known as rectifying contact. So you can so the rectified voltage, they conduct the conduct the correct current in one of only one of the direction, and ohmic contact conduct the current in both the directions. So basically for like these ohmic contacts are important basically when you want to there are like different kind of devices like Schottky barrier diode. So you ideally want to conduct the current in one of the direction, and you don't want to conduct the current in the other direction. So there you need Schottky contact, and an ohmic contact where you need is suppose you are making any device like NPN transistor or PN junction or any other junction. So basically, when you want to take out, so this is like that. This is substrate. Let's say P type, and you make N well, and then like this make a junction, and then you make a contact here with the aluminum also. So and also in the substrate you make the contact. So basically to make this PN junction possible, you need this contact as the ohmic contact, let's say. So like this kind of contact. So let's define what happened in case of Schottky contact. So now like if there are two different case. So basically like if just yeah. So now if semiconductor work function is smaller than the metal wave work function, so then it will be a Schottky contact. And if semiconductor work function is greater than the metal work function, then it is a ohmic contact. We will see how. So now let's say our semiconductor work function is larger compared to the metal work function. So if we draw the band diagram, then this is the if this is the vacuum level, then let's say this is the boundary. So if we draw the band of this is a metal phi m, and because phi s is let's say we are drawing for uh, yeah. So let's say we are drawing for Schottky junction. So we the semiconductor work function is smaller compared to metal work function. So this is EF, and this, as you can see, this phi s is smaller compared to the phi m. And with respect to this Fermi level, you can draw the conduction band and valence band. So you can draw the conduction EC. This is EC, and this again you can draw. So depending on the whether the if this is N type or P type, you will see like the different kind of junction. So this now if we draw these are the band diagram which you need not make contact. So if you make contact, then equilibrium condition will prevail. Then you need to draw this EF as constant. So EF in the metal side and EF in the uh, uh, Fermi side, EF in the metal side and EF in the semiconductor side will be uniform. And if you make EC here in the bulk, the condition of neutral region will prevail, and in the metal, this the Fermi level will remain same. And here, because this level, this Schottky barrier will remain same. This is phi b, and here some band bending will be there. So as you can see, like this kind of junction, there is the electron will feel this barrier, so they can't cross this junction. So that's why this in one direction this will block the conduction, block the current, and in another other direction. So in other direction, hole will take part in the conduction, and they will recombine with the electron in the metal, and the conduction will take place in other side of the junction. Or if you pull this barrier down, then like this barrier this barrier will this electron will this barrier will get reduced, and you will see a flow of current in the Schottky barrier junction. And still you will see some threshold after this start like conducting, and that is known as the Schottky barrier threshold. So with this now like if you consider the case with where the phi s semiconductor work function is larger compared to the metal work function. So this is phi s. If this is larger, then if you draw the band diagram, it will look like this. So basically this barrier will remain same, and this will flow like this. So in the bulk region, the so just so in the bulk, this will remain, this will be the Fermi level. As you can see, this these electrons does not see any barrier, so you can apply positive and negative bias, and you will see a flow of current in both the directions. So electron can jump from here, and you will see the flow of current if you apply any potential difference uh, uh, kind of it. So this is the different region of operation for Schottky barrier diode. So these are the uh, ohmic and Schottky contact. So basically that you can you can so these are very important for the devices, even in MOS case. So you can make like this gate, and gate is basically dielectric, and this source and drain, you make a ohmic contact in the source drain region. So this is n plus, and this is n plus, and this is p. So basically, you make a ohmic contact in source and drain region, so that you can have effective conduction in both the direction. So from source to drain, and drain to source, it just form a ohmic junction kind of thing. So now, in the class, whatever other important device was discussed in the MOS capacitor. So basically, MOS capacitor is very important in the functioning of metal oxide semiconductor junction. So basically, like if you take the gate region of the dielectric, basically define this. So if you take cross section across this device, and if you take this cross section, if you take this cross section, then you will see like here this metal is there, plus oxide and semiconductor is there. So all the turn on characteristics and other characteristics of the MOSFET are defined by this MOS capacitor, which forms in between the gate, oxide and source substrate region. So basically, for simplification, we can draw the MOS cap as like this. So uh, this is this is metal, and this is oxide, and this is semiconductor. So if you take any N type or P type, any semiconductor you can make. So that that kind of junction is known as a metal oxide semiconductor. And since this oxide will make a capacitor, so that's why it's known as a metal oxide capacitor. And this the capacitance of this MOSFET, this devices vary with application in applying bias. So it is more than that in certain region of operation, it is more than just parallel plate capacitance of the device. So this is ultimately important in understanding the device operation or threshold characteristics or turn on characteristics of the MOSFET, or metal oxide semiconductor, or other FET devices, basically high electron field effect transistors, or other other devices. So this is quite an important, and it has because now almost all the logic technologies and those are based on like FET based. So FET base. That's why it's quite an important device. So basically, like if we want to draw the band diagram, so the ideal. So in this class, the ideal MOSFET was discussed. So ideal MOSFET, some properties are there. So basically, first thing is metal work function is equals to the semiconductor work function. So basically, it's not a bending, and the interface trap charge is zero. So this interface is very pristine, but in practical case or very experimental case, this may not be the case. There are trap charges because of the uh, just So basically, your interface is free of all charges, and that case we will consider. So ideally, this let's draw the band diagram. Band diagram for this metal oxide semiconductor case. If we draw to draw the band diagram, so basically you need to consider each interface. Each interface you need to consider, and then this oxide will have high band gap, and this metal region will have only Fermi level, and this semiconductor has will having a comparatively lower band gap plus doping. So if you draw the band diagram, so in the when you did not make any contact, so this band diagram will look like this. So this you will see a large band gap here, and there is certain band offset between like this EC, and this is EV, and this is the EF, and you can draw this as a EF. So basically, now 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 this is the band diagram, and if you consider the ideal junction, so this EF in the metal side is same as the EF uh, in the semiconductor side, and if you apply a so there are different region of operation of the MOSFET. So basically, these are accumulation, and other is depletion, and then is a inversion, and then there is a strong inversion. So this kind of region. So if you consider this as a let's consider this as a p-type substrate. So let's draw the EC and EF like the EF, and this is the conduction band EC, and this is the valence band this is the valence band EV, and this is the conduction band. And as you apply so what will happen is uh, so uh, so now if you apply a positive gauge bias, so this Fermi level will goes down in this side. So if you are applying a positive battery across this junction, so then this potential in the in the metal side will go down, and it will be like this. So if you have applied like this, and this gap will remain constant, and it will behave like this. So in the bulk it will remain constant, and in the this it will be like this. And similarly this EI level also will bend, and this is known as the, like, up to a certain time, this is known as the depletion region, because this band bending is there. And the this surface, the interface at this metal and oxide junction is becoming more n type, because the conduction band is becoming more closer to the to the Fermi level, so it's becoming more n type. And those electrons in this p-type substrate will come by depleting the substrate. So this is known as the depletion region. And other is, if you apply a negative bias, so this electron will pull toward the junction, and they will accumulate at that boundary, and you will see the accumulation region. Similarly, when you apply a strong bias such that this bending is equals to two times the surface potential. So basically, this phi f is kt ln nd by ni. So basically, this is your known as your surface potential. And the case for inversion region to occur is when this band bending is become 2 phi f. So basically, like this, at the interface, basically EI will become higher, will become lower compared to EF. So we can say the inversion has taken place, and the interface has becoming from n type to from p type to n type, or n type to p type. So that is known as the inversion layer. So that is the surface potential uh, psi f is basically 2 times phi of f, and that is the boundary for the inversion layer. So depending on the substrate, basically we will see inversion or depletion with the positive or negative application of details. And you can see this uh, uh, this so like you can see a different region of operation in the in the actual device. So with this, let's just move out to so different kind of regions exist, and for details you see the lecture in the whatever uploaded in the content. And then like if you have doubt, then you can ask in next class, or you can start reading some books related to the MOSFET. So let's start with the problems of solving. So if you have any doubt, then if you please ask. I will pause for some time, and then if you don't have any doubt, then we will start the problem solving session. Uh, I will pause it for a minute, and then if you don't have any doubt, then we will start. Okay, so let's just get started. The Which of the following is defined as the work function of the material? So, so as we have discussed, or as we discussed in the class, so the energy required to move an electron from EC to the vacuum level, the energy required to move an electron from EV to the vacuum level, and the energy required from to move an electron So this EC to the vacuum level is defined as the electron affinity. So this is wrong option. The energy required, that does not have any significance, and the energy required to move an electron from EF to vacuum level is defined in the work function, and this is the correct option. And last choices are energy required to move an electron from EF to EC. This is wrong. So, and the energy required to move an electron from EF to EV, this is also wrong. So, this is just by definition type of question. I hope it's quite clear, whatever explanation I have. So, this consider a short key. Consider a so let's move to next problem. Consider a Schottky diode made from metal and a N-type semiconductor. The doping of the so the doping of the Schottky diode made from a metal and N-type semiconductor. The doping of the semiconductor follows an abrupt profile, and the work function of the metal phi m is greater than that of semiconductor. Uh, the metal is greater than the semiconductor. The charge configuration of sub device is shown in the figure. Um, so this so let's draw the band diagram. So basically let's draw the non-contact band diagram. So if you draw the vacuum level, so this is a vacuum level, and then you draw the this is the metal work function, and so this and it is given that semi metal work function is greater than the uh, semiconductor work function. So this is psi s. So now this so this is EF, and this is EF in metal. So now since now just so now there is like so now the since the in semiconductor the Fermi level is lying at the higher energy, so there will be a flow of electron until unless the Fermi levels aligns. So that like if you draw the equilibrium band diagram, it will become like this. So it will be like this, and this is the Fermi level, and this is N type, and this is also N type, and you can see like the at the interface the EC minus EF will become larger, and as you go EC minus EF will reach to the equilibrium. So that's why like that you can say like the at the interface the semiconductor become less N type, which means that it has become like it the electron has been depleted. So the electron depletion has taken place, and because of that, if you consider a uniform charge doping, then basically, and this the electron transfer at in the metal side, basically electron will accumulate at the interface. So you can draw the charge picture, and since if we assume a uniform doping, so so n-type semiconductor uh, follows an abrupt profile, and the so this doping profile is given, and this it will the charge density will be q and d this side, and it will be similar total charge will be there in this side. So the charge density in this case, so as you can see, like the correct option is here this is given as uh, so yeah, so this is wrong. So this is in the p side, the charge will not be there. So in metal case, like because there are infinite numbers of electrons are there, so all depletion will not take place, only the interface charge will occur. And this charge density in this option, so this is wrong. And this charge density shows a linear increase, that is wrong, because the in case of uniform doping the charge density will be a constant, so this is also wrong. And after depleting the carrier, basically the immobile charge ion in case of n-type junctions are positive donors, so this the charge here will be a positive charge. So you with the C option you can see the charge is q and d plus q and d, and it extend up to xn, and at the interface minus delta charge is there. So this looks like correct option, and other option is right side is correct, but left side you will see the charge profile like this if you have only if you have gradient in doping or the that thing. So but this left side is the metal, so you can say safely say this side, this is also one of the wrong option. So the correct option is C1, and that is the correct option. So let's move to next problem. So consider a Schottky diode made from a metal and n-type semiconductor, and the doping profile of a follow uh, linearly graded profile. So now this is linearly graded, and the work function of the metal is greater than that of semiconductor work function. The charge configuration is in such device is given as. So, in the case of linearly grading charge profile, so your rho s is basically some kx. So basically, it just the charge profile in this side it will be a step, it will be a delta function, but the in the semiconductor side, because the doping is non-uniform, it will be a linearly increasing or decreasing kind of curve. So that is that is the profile. So this first answer is wrong, second answer is correct, and third answer is wrong because that was the case for uniform doping, and fourth answer is wrong because that depletion can't be there in the metal side, because metal has infinitely large pool of electrons in the semiconductor. So if you want to consider like what is the ratio, so typically suppose you take the like the single electron kind of metals, like let's say aluminum or those we have 1 ampere electron. So the density is approximately 10 to the power 20 to 10 to the power 22 atoms per centimeter cube, and if each atom is given 1 electron, then you will see 10 to the power 20 to 22 electrons per centimeter cube. And in the case of semiconductor, you do around 10 power 18 or 10 power 16, 10 to power 16 to 10 power 18 per centimeter cube doping. So the charges are there, like in this configuration, the atoms are this density dopant atom. And if you consider a single atom, a single electron containing dopant, then you will see like the 10 to the power 16 to 18 per centimeter cube electron density. And you can see this number. So basically, it's two orders of difference in the conduction. So that's why there will be like two order of difference in the depletion width and so on. So if even if you consider a depletion width then basically this side of junction will be having like 100 times less depletion rate compared to that, and that fairly you can consider as a delta doping or delta charge case actually. So because of those this large difference in electrons and in hole concentration, you can see like the depletion width in the metal side is practically non-existent. And some kind of technologies actually like that polysilicon gate and those self-aligned gate technologies, because in the gate you use heavily doped polysilicon, so there are some kind of depletions are there in the even in the gate region. So that you need to consider those kind of scenarios separate. So the correct answer will be B option. So yeah, so this was this part. So let's move to next problem. Uh, so this the equilibrium energy band diagram for an ideal metal semiconductor contact is shown in figure below. Answer the following question based on the band diagram. So the as we have seen in the case like this, so so the this case is basically the Schottky case, and because this Schottky barrier become, and this kind of cases only happen like with when you have metal uh, like metal Fermi level greater than the semiconductor work function. Metal work function is larger than the semiconductor work function, and this kind of case will happen. So the figure A band diagram is basically phi m is greater than phi s, and as we have seen that this will behave like a rectifying contact. So if you so so how it will behave a rectifying contact, if you apply a negative bias, so this will move up. So you are applying, so let's say this is the metal and this is the semiconductor. If you are applying a negative bias, then basically this potential will get increased, or so this potential will get decreased, or then like your the conduction band energy is basically minus V of potential divided by Q, and since this potential is negative, so the energy will get increased. So that's why you will, when you apply a negative bias, you will see upward in the that band diagram, and so this band will move up, and so this barrier will also get increased, and this electron will see a more barrier, and so that the current is reduced. In other case, if you apply a positive bias, so that this barrier will get reduced, and this barrier will become a bit lower compared to the normal case, and so that electron now can go jump this barrier, and that thermionic emission will take place, and that you will see a conduction current and so on. So that you will see a a this kind of behavior will be like a rectifying or Schottky contact. This behavior will be, so the correct answer is phi m is greater than phi s, and this is a rectifying contact. So that same problem, the relation between metal and semiconductor work function in the contact form in figure B is, so basically this is the reverse case. Basically, if your semiconductor work function is larger, so your Fermi level will move up, and then like this this will won't the electron won't see any barrier. So if you apply any positive bias, electron will jump, and if you apply any other in the other direction like negative bias, then electron will flow from here to here, because this barrier is practically non-existent. So this is the case for phi metal. So this is the case of phi metal is less than phi semiconductor, and this is no, just wait. So this is this is this is the correct answer is the ohmic contact, and this is not correct answer. So the this case the correct answer is ohmic, and this will behave like a ohmic contact. So with that, let's move to next problem. The next problem talks about the copper is deposited onto n-type silicon substrate to form an ideal Schottky diode. The work function of the copper is phi m equals to 4.65 electron volt, and the electron affinity of silicon is 4.3 electron volt. The Schottky barrier height is given as this. So the Schottky barrier height is given as work function of metal minus electron affinity of semiconductors, and work function of metal is given as 4.65, and the electron affinity is given as 4.03, and will become 0.62 electron volt. And this is the second is the correct answer, and this was fairly straightforward problem if you understood the concept properly. So the built-in potential in the copper Schottky diode is uh, this volt, and this is given as Nd Nd is 10 power 16, and Ni is 10 power 10, and then basically to calculate the built-in voltage, so basically you need to draw the equilibrium band diagram. So basically if you draw this, the so just yeah, so this if you draw this is the phi barrier phi b, and this is just so this is phi b, and this is basically the banding is this q time dbi plus this ec minus ef. So you can write q time dbi plus uh, ec minus ef uh, equals to phi b, and the built-in potential you can calculate, and also you can calculate what is the just so you know the Schottky barrier height, and if you know this so basically if you know this, and if you know ec minus ef, that how you can calculate. So basically this so n electron concentration is given as ni exponential of ni exponential of uh, ni exponential of um, ec minus ef by kbt. And if you calculate the ec minus ef from this, so you can calculate ec minus ef as n you can take as nd, and that you can calculate kt ln nd by ni. So that you can, if you put a proper value, nd is 10 power 16, so this kt is 25 kt ln, so nd is 10 power 16 and this is 10 power 10. So this become 6 time kt ln 10, and this number you remember, this is 60 milli electron volt, this is 60 milli electron volt, and this you will reach 0.36 electron volt. You will reach 0.36 electron volt, and then this you can put in this equation. So basically built-in voltage, like VBI, you can calculate time VBI equals to phi b. Phi b is given as 0.62. So this is no, just wait. So 6, so this will become 0.62 minus uh, 0.62 minus EC minus EF, that you can calculate 0.636, and that if you substitute, you will reach around point you will reach around uh, so this so uh, no, no, this is EG minus EI. So also, yeah, so no, no, this is EG minus EI. Actually, this is not EC minus EI. This is EG minus EEC minus. So this is EI minus EF. So so this is EI minus EF. So basically, it will become minus EI minus EF, and this you will reach at 36 electron volt. This EF minus, so this minus of this will become 0.36 electron volt, and you can, to calculate EC minus EF, basically you need to subtract from EG by 2 minus EF minus EI. So if you calculate 0.52 minus 0.36, this will become so this will become 6, and this will become 0.26 electron volt. And if you put 26 here, then you will reach around uh, uh, 48 0.48 48 electron volt, and the correct answer will be around 4 correct answer will be around, like, the most closest answer is 0.43 electron volt. So just wait, 6, this is 6, uh, 5.5, no, this is 5.5, and this is basically it's like 2.9, and this will become finally, this is 2.9, and this will become finally 0.43 electron volt, and this you can write VBI as 0.43 volt. So that is the built-in potential. Yeah, so for zero applied voltage, the depletion width, which is the semiconductor due to the formation of copper Schottky junction, and that you can calculate. So basically, the VBI you can calculate from the charge also. So if you integrate, so if you take the uniform charge like QND, so the charge profile will be uniform up to xn. So this QND, if you dE by dx equals to QND by epsilon, if you integrate this, so you will reach that ED, basically E at 0 is basically QND times xn by epsilon, and if you or E of x, you can write E of x, you can write QND by epsilon x minus xn. So that you can write, and then if you integrate one more time, you can reach the potential drop across this semiconductor, and from that you can calculate the depletion width, and depletion will come out as qnd by 2 epsilon silicon times w square. So this w, you can calculate square root of 2 epsilon si by qnd times vbi, and then you can calculate basically from this equation, uh, you can calculate the depletion width, and which you if you put the values correctly, you will find that this depletion width is 2.37 something micrometer. So that epsilon si and those are given in the problem, so the correct answer is A. So the simplified band diagram for a MOSFET are shown in figure below. Match the following energy band diagram from 1 to 3 with corresponding substrate type and applied gate voltage VG and the bias condition. So for each of the MOSFET band diagram in the figure, identify type of MOSFET and the substrate used. So to find basically to find which type of MOSFET, so basically, so if the substrate is P type, then it is NMOS, because then your like the basically NMOS is this, NMOS or PMOS is defined as like the channel is which kind of carrier. So in NMOS, the channel region is electron, and the PMOS, the channel region is holes, and the substrate is basically to deplete the substrate you need p type substrate, so that you need and for this you need n type substrate. So for so let's see like what are the this is so so as you can see, like this gate level is higher compared to the Fermi level, and this Fermi level lies closer to the valence band, and this is p-type substrate, and this because of the application of the uh, uh, application of the uh, negative gate bias. The So this is the substrate is n p type, and you can see there is, as you apply a gate bias. So this this you can see this is nmos basically. So the electron will be so the surface is becoming more n type at the interface, so it is nmos, and the carrier type is p type. So the first is nmos and p type, and the second is pmos because the Fermi level lies closer to the conduction band, so this is n type substrate, and that like the inversion of these holes will take place by application of negative gate bias voltage, and that the banding is there, and like the depletion of hole will take place, and you will see the type is n type, and the type of MOSFET is PMOS. Similarly, you can see in this case the with the application of like the gate bias, you can see like this type is n type, but this band bending is up with application of the gate bias. So that means this whole accumulation, whole depletion is there, and electron accumulation is there. So basically, this is kind of n type and PMOS kind of thing there. So because this N-type substrate is there. So the correct answer is this one. Fourth one. So this is the correct answer. identify the sign of applied gate voltage and the bias condition from the this thing. So this, as you can see, like this, the interface is getting inverted, but not, it's not that inverted that the surface layer, the surface control potential is such that the interface has become from p type to n type. It's not that high. So basically, you are applying a positive gas bias, and it's in the depletion region, and that so in the second case, basically you can see like this, the surface, you are applying negative gate bias, and so that's why this level is moving up, and you can see the interface is inverted, like this is phi f and this is also phi f. So this total has become 2 phi f. So this total has become 2 phi f, and you can say this surface is becoming inverted. So you can say this is in the inversion region, and because this band is moving up, so you can write this as a this is negative bias. So the correct answer is fourth one, negative bias and inversion. And in the same case, like you can see, like this, the inversion is not so high, so that it's invert the surface potential to minus 2 phi f. It just become totally depleted. EI has become equals to EF, and that you can characterize by the depletion. And since the band is moving up, so the voltage apply is negative. So the correct answer is negative and depletion. So the correct full answer is this one. If you choose it correctly, this is the correct answer. So you can choose like this option correctly. Other options are wrong with the same argument. If you see. So these were the problems from like for this week actually. So let me discuss a bit more cases for. Let me discuss few more cases of band diagram. So if you have doubt, then you can ask, or so yeah. So if you have a doubt, then you can ask. I will pause for some time, or otherwise we can end this session and we will meet next week, same time at the same platform. Uh, so that's all from my side. Thank you so much. Hello, hi Lakshmi. You joined recently. You have any doubt? I have almost reached at the end of the session. So you have any doubt? Okay, so if you have any doubt, then you can ask. I will pause for some time, and related to any content covered in the recent time. If you hello. Okay, so I think so. If you have any doubt related to the previous session or this session, you can ask, or let me give a brief with more detail of MOSCAP actually. So basically, like different region of operation of MOSCAP, if you consider, so basically, if you if you can consider, so different region of operation, like let's say you have a a this is a metal, and this is oxide, and this is semiconductor. So different. Now let's assume like the metal work function is equals to the semiconductor work function. So three different case we will consider. Let's say so so three different cases we will consider. First, we will consider we apply a gate bias here. So here we apply a gate bias, and this is VG. So this is VG. So three cases are there. So first case is VG is less than zero. So this is P type substrate. So this is P type substrate. So this is NMOS basically. So the so if the substrate is p type, then it will become NMOS, and that and like now the gate voltage is applied such that gate voltage is positive but less than the threshold voltage, or the voltage required to invert the channel, and gate voltage VG is applied greater to the threshold voltage. So these three different case. First is the accumulation case, and other is the depletion case, and other one is the inversion case. So what happens is we explain by a band diagram. So basically, if you draw the band diagram, so if you draw the correct way of drawing the band diagram is basically you draw the vacuum level first, and then you basically write uh, all the energy level, Fermi level. So this is the Fermi level in metal, and this is the Fermi level in semiconductor. So EFS. So since the phi metal is given as same as phi semiconductor, so this level will be phi s. So now the Fermi level will be aligned, and since this is the p-type substrate, so this the Fermi level in the bulk will lie uh, closer to the conduction band, and this is the conduction band, and this is the valence band. So this is the equilibrium band diagram. So now what happens is so this is at the VG equals to 0 case. So since this is the like now this the junction is ideal, so that because of that you assume this is very pristine interface. So there are no interface trap. Traps, and that traps happens because like suddenly if you are doing like some diffusion oxidation or any diffusion or any doping any growth process, or you are growing the oxide, so you turn off the gas suddenly. So like there are some bonds which are not satisfied, that will contribute to the fixed oxide charges in the case of semiconductors. And also like there like the because the improper deposition or growth process, some ions may be introduced in within the oxide of growth also, so that also contribute to a charge, or they can be mobile charge like with lighter atom like sodium and those kind of things. And also there can be like the fixed charges which remains fixed uh, within the oxide region. So here we assume like the oxide is free of any mobile or immobile immobile charge carriers, and interface is free of traps. So basically if the interface is free of trap, and you don't have any like mobile charge carriers, then this oxide will behave a perfect insulator. So you can take like the while applying the Gauss law, you can take this dE by dx equals to rho by epsilon minus. So this rho you can take as a zero, so you can write directly dE by dx equals to zero equation you can solve. So this is the Laplace equation. So now what will happen if we apply the gate bias? So if we apply the positive gate bias, what will happen? So if we apply the gate bias, so here the positive potential is there. So this is the at the positive gate potential. If you apply positive, let's first apply the negative way. So this is at the negative gate potential, and your E is minus of B by Q. Uh, then like the energy will be band diagram will move up or in the positive direction. So that in that case basically it just move like this. So the band will move up. Here it will move up. So just wait, I draw my bit oversimplified. So here basically you need to consider just so this so you need to consider at this interface also. So this interface also, so here this EFM here, but here it will be the band of oxide band gap, and that basically Q. So now what you do is you apply a negative gate bias voltage. So this will become minus QVG, and that so the this because of this offset will remain same. And if you can draw this band diagram, and that this some potential drop will occur across this region, and this offset also will remain same. So that you can see it's like some bending in the upward direction in this case. So like just the similar you will see here. So similar he will see here kind of. So this, as you can see, like the if you draw this ent so this is p type substrate, and you are see like now at the interface this EF and conduction band are coming much closer. So this is interface is becoming more p type, and since this is a p type substrate, so like a large number of holes are available, so they will like move this to this side, and they will form like a sheet charge. So this direction is the scale is at the log scale, but if you see it the linear scale, this will look like very thin sheet of charge carriers over there. So that you can just assume like this operation as a accumulation region, and this kind of the capacitance which forms here will be the uh, accumulation capacity. Now, if you apply a negative gauge bias, what will happen is the band will move down. So this band will move down, and similarly here, instead of this, the band will move like this. The band will move like this. So the band will move like this. So, and that you can write like this. Similarly here. So the band will move like this. So as you can see, like the band like the interface is becoming more n type. It has becoming because the conduction band is coming more closer to the Fermi level is becoming more closer to the conduction band, or the valence band is moving away from the Fermi level. So you can say like that depletion like the so there the holes holes will move to this side, or the depletion of the charge, or depletion of the holes is taking place to increase the n type of charge carriers. And that you can basically see like that the this so this that's why this region is known like as the depletion region, because like now we are depleting the majority charge carriers, and interface is becoming more n type. So this region is known as the depletion region. And now if you have, this is the surface potential phi f, and if you apply a bias, then this banding also will be follow the similar trend to this banding. And that at the if you keep increasing the gate bias, so this will become more and more banding will be there. After a certain threshold, this will become like this bending will become 2 times if, and then dbi will become 2 times of psi f, and that is known as the boundary of the inversion layer. Because as you can see, like the now the ei label is lies closer to like below the Fermi level by phi f amount. So that's why you can say now from p type the substrate has become inverted, and it hasn't become in n type from p type. So it has become n type from p type. So this is the inversion region. This so that is the inversion region. And after that, if you apply a negative gas bias, so like some that we will discuss later, like what is the strong inversion region. So these are the main regime of operation for MOSCAP. So basically, these are the accumulation, depletion, and inversion. So that was the MOSCAP bit more detail compared to the initial I have discussed. So this was the yeah. So that was the that's all from my side. If you have any doubt, you can ask, or we will end this session. Hello. Yeah, Sanjeev, you are not audible. Are you speaking? Use mobile. Yeah, yeah, yeah. Mhm. And get, P-type and N-type. Mhm. Changing this, uh, what happens? Then what happens? P-type to N-type and N-type to P-type. There will be so uh, uh, there will be compromise. There have solution. Okay, so you are confused about whether what will happen to uh, uh, can I yeah explain you? You just explain, yeah. Uh, how you okay. So you are going to write, or you are sharing something? Uh, Hello. Yeah. Yeah. Yeah.
Is uh, when we get a p type to n type
Yeah.
and
Hmm.
n type to p type
Hmm.
automatically
Your doubt is
depending.
uh, uh, your voice is bit breaking. So you are saying like, can you get the N type to P type automatically, right? Uh, you don't need to change the doping or anything. You don't. Hello, is that your doubt? Is that your doubt? Hello, hello.
Sir,
Yeah, yeah. Hello. Yeah. Now am I audible? Now am I audible?
audible, sir.
Yeah. So is that your doubt? Is that your doubt?
Doubt.
Can you speak again about your doubt?
Have a doubt, sir. Some
So can you again explain it?
second.
Uh, Hello. Uh, Hello. Am I audible?
हेलो सर
Yeah.
ऑडिबल सर
Uh,
सर अगर आप मोबाइल को चार्ज करें
uh,
तो पूरा मतलब पी टाइप और एन टाइप ऑटोमेटिकली हैपन
okay. Yeah.
आई
So
मीन
you are getting confused. So basically, like you are saying, uh, basically how it's becoming from N type to P type automatically, right?
यस सर यस सर
Yeah. So basically,
दैट इज माय डाउट
yeah. So that like what happens is, see, so now if you consider actually, even in equilibrium case, so like the so basically like this suppose p type substrate is given. So what happens is, so this p type substrate is given. So it has, so now to invert the channel you need electrons actually, right? So, but the substrate has, let's say p type substrate is there, it has any number of holes are there, but the electrons are, if you calculate the electrons, then it is Ni square by Na. So these are, like, let's say Ni is 10 power 10 per centimeter cube, then let's say Na is if with 10 power 16, then your like this Ni is 10 power 4 per centimeter. So even in this condition, like that, your the electrons are there. So basically, so how you generate the charges, by by depleting those substrate actually. So depleting the substrate means you remove the holes from here. So if you remove the holes, then electron will get increased actually in equilibrium if you. So in equilibrium, N into P is basically Ni square. N into P is equal to Ni square. So if you deplete the holes from the substrate, so if you move the hole from this, let's say, at this interface to the bulk in this region. So if you remove some holes from there, so this P will get down and corresponding will increase in electrons. So basically, what you are doing is you are depleting the majority charge carrier and generating the minority charge carriers, and also and this electrons actually in electrons you will see in next or some higher order group. So they can come in variety of different way. So one case is this depleting this. Other is if you shine a light. So there are electron hole pair generation, and that also can generate these electrons actually. And especially and this particularly in the MOSFET case, actually MOSFET is basically if you draw the band diagram, so this is like this n plus and n plus and this p plus. So basically so MOSFET case, there is one this metal oxide semiconductor here, but this side is a p-n junction is also there. This so basically, this charge will come like as you apply this bias positive. Then after some time, this barrier will get reduced, and you will get a depletion charge from there. So that's what like in the threshold condition. So this is bit more forward. So you can read in some books or those. So like this can come in variety of different region actually. So this and this you can see very experimentally actually that's how you generate actually. So is that like partially answer your query? Hello.
Okay, sir.
You get, yeah, so you are not doing doping, just you are changing the electrostatics, and you are making n-type more n-type by depleting this substrate actually. So is that answer your query? So you think about it. If you don't like even not convinced, then I may also be prepared so to explain, or you can ask in next session actually. So you think about it. If even if you now you if you have any doubt, like just let me know. So what is your confusion now, or is it clear? Well, still get confused because this kind of devices courses we sometimes we what will happen is we thought like we get understanding, but when we keep our notes or book aside, then you again get confused, and then you say, oh, this electron will go here, this will go there. I am confused. This used to happen for me quite a lot in my UG. So that's all. Like that, I think you should keep thinking about those things actually, and keep eating like the like proper food.
Yes,
Okay.
sir. I have.
Yes. Sorry, you were saying something. Yeah.
Sir, I have need some reference,
Okay.
some more details.
Um, reference. So you can read like this Benji's treatment actually. Right.
Sir, basically, practically, what happens when we mobile to charge everything? What was in this? Uh, then
Hmm.
there will be. uh, what, what will be the structure of p-type and n-type and
Structure
band
band diagram. Hmm.
diagram
So
and p-type
you
and n-type?
uh, so like PN junction band diagram.
Yes, sir. Yes.
So you are talking about like uh, practically how the PN junction band diagrams are there, or is that your doubt? Hello.
The doubt, and yes,
You can talk in Hindi also if you are comfortable. Then you can talk in Hindi also. So.
have doubt.
Uh,
P-I-N.
hello. 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 I think. Hello.
Well, sir, okay. Okay, sir.
Yeah. So I
Yes,
missed.
sir.
Yeah. I think I.
Yes, sir. Audible, sir.
Yeah. Yeah. Now you are audible. Yeah. Yeah. Tell speak. Tell me. Yeah.
Sir.
Uh, so
Sir,
uh,
I basically
uh,
uh, use of device.
uh, hmm. What is the use of semiconductor devices? Hello.
Sir,
Just wait. Actually.
yeah, what is simply current.
Uh, just wait. My connection is a bit loose. I
Yes,
just lost my connection. Just wait for.
practically, the conductor
Hello. Hello. Now I am I audible?
yes, sir, audible, sir.
So what you were asking?
Sir, my problem is alternative current when you use the mobile charging.
Hmm.
There will be alternative current, AC current.
Uh,
Then uh, uh, P type and N type. Uh, uh,
hmm.
from P type to N type and N type to P type
Hmm.
automatically happens. Is this right, sir, or not?
No, 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 no. You are saying like if you are flowing AC current, uh, actually, then what will happen?
Yes.
Yeah, right. If you
Yes,
are,
sir.
if you are so,
Yes, sir.
let me just explain. So, what is happen actually? So, like this you see, like when you see, like when you do a like uh, like the capacitance voltage characteristic actually. So, what happens is this is bit more forward, but let me just give it give it a try. So this thing. So now basically what you are applying is, let's say, you are applying is, let's say, uh, you are applying a positive, so let's say you are applying a DC plus AC voltage. So what has happened? So like you apply a very small signal actually. So what will happen is, so that so basically, like this DC level will cause a like depletion because of the band bending. So now what will the effect of this AC signal will be? So this will change in charge actually. So this will slowly deplete this carrier actually. So this will like move like the depletion will move around actually. So that you will see like in the that depends like the what is the so that depends like how these carriers are generated. If your carriers are generated by the thermal generation, then basically this is a very slow process. Then you will see basically like if you plot the capacitance voltage characteristic, then if you take MOS cap actually, so this will this like in the accumulation the capacitance will be this. And if you take just wait. So if you take depletion, it will be like this. For low frequency case, this the high frequency case, this will become lower because like this can't respond to the like very high frequency actually. So because this thermal generation becomes slower at high frequency actually. You can calculate the rate practically, but see, like nowadays, our devices operate at like let's say your laptop or those practical devices, they are operating at gigahertz frequency. So and that they use same kind of MOSFET or FinFET or whatever field effect transistors. So like that like so how they are able to operate that fast actually. So in case of MOSFET, those are special device basically. So this charge basically does not come just by depleting the substrate. So up to a certain threshold, it comes up depleting the surface. But like here, this PN barrier forms actually. So if you are applying a positive gate bias at this, so this surface potential of p-type substrate will get increased. So basically, you are basically forward biasing this PN junction, and this barrier will become lower, and this will inject a charge. So this does not has any frequency base because this n plus region has very a huge pile of charge carrier. So this barrier lowering will transfer a charge at very high frequency. So this that's how your charge will operate, and this like this the MOSFET basically it just respond to the like infinitesimal charge you increase basically by applying this AC plus DC signal actually. So is that answer your query?
Okay, sir.
So, did you get like what I am trying to say actually? So basically, when you apply AC signal,
Yes,
you're
sir, I have got.
okay. So, yeah. So that was the uh, uh, so you have any other doubt?
Not now, sir.
Okay, fine. Okay, I think then let's just end this session for today. Thank you so much for listening. We will meet next week same time at the same platform. Bye bye. Have a nice time. Thank you so much. Uh,
Thank you, sir.
okay, welcome.
Thank you, sir.
Welcome.